Okay, can you hear me in the back? Mostly? Okay. So this is the last new material for exam 2. So Thursday will be review. Get through these slides today. And we'll be looking at the virtual memory system. Okay. Maybe at some point it will decide to. There we go. Okay, so brief review. Been wandering around in the cache for a bit. We're not going to really spend any particular amount of time. Main memory architectures are their own interesting construction. Certainly, if you want to look at new things that are happening there these days, the move to high bandwidth memory, some other interesting things there, storage class memories and so forth. But we're going to mostly be looking at this piece here today. How do you virtualize the physical resources of your machine, which are far smaller than the potential things that you could be naming inside your program? Okay. So hopefully we all recall how the different portions of the memory hierarchy are managed. So the registers are being handled at the instruction level. The cache, as we've just seen, is all done in hardware. And the virtual memory system, in contrast, is going to be a collaboration between hardware and software. Exactly which parts of this happen in hardware and which parts happen in software vary from ISA to ISA. Right? So for instance, TLB management in MIPS is, well, there is a hardware element here that's helping. All this management is in software. x86 has a hardware page walker. Actually Turing complete. You can actually execute entire programs on your page walker. Fun stuff. While we will be talking about paging and going off to these secondary devices, we won't actually be talking about long-term storage or any of that data. So recall that your programs don't talk about real memory unless you're spending all your time doing embedded system stuff. Right? Your default piece of software that you're running on a thing that you think of as a computer has a very simple abstraction of memory. It's one enormous array of bytes. Part of it is nearer or farther or faster or slower, i.e. it is random access. This is of course not actually true, and to some great degree neither is the first one in terms of what you're actually building. So that's what we're referring to as an address space. So in most models of interest, your program has one address space, right? There's one address space per process. There might be multiple threads of execution within the same process that share an address space, or they might share part of an address space. So threads do have some thread local memory. Right? They have different names for some of the same pieces. Right? And so all this user mode stuff that we're talking about here is virtual, right? It doesn't actually have any real understanding of where the data that it is referencing is actually backed by any physical component of the machine. Right? It just says address 5 million, get me some bytes. Right? Where is address 5 million? I don't know, I don't have to know, and I'm very happy that I don't have to know. That lets me write my program in a reasonable way. Right? But at some point, your hardware actually has to figure out where in this system is the data you just requested. Right? There needs to be some sort of relationship between the virtual and the physical memory. And traditionally, managing that has been the job of the operating system, right? At least ever since back in the IBM System 360 days. Okay. There's some other things that go along with this. We're not going to dwell on them deeply now, but if you want to think about a lot of security concerns, right? A lot of the ways that you ensure robustness of your system, these tend to be tacked onto the implementation of the virtual memory system, right? Your protection bits get added on to all the other things your TLB needs to do to manage just the translation, right? Can you execute the data on a page? Is it write only? Is it read only? Right? All these other sorts of things have been bolted on. They are not necessarily coupled. You could handle them with separate pieces. It is reasonable to put them where they are, and you can sort of assume that a lot of this protection is going on in the virtualization process itself. So if you ever are interested in looking at how security plays out in modern machines, you are going to have to spend a lot of time staring at the actual implementations of virtual memory systems. So for instance, how many people have ever heard of SGX? Okay, so none of you care about trusted computing in the cloud. You're just going to trust that the cloud is perfectly benign and has no interest in looking at any of the data or computation that you're doing out there. Right. In Google, Amazon, and Meta, we believe, even though they're firing everyone. Right. Okay. Well, look up SGX at some point. It's an interesting thing. Okay. So in practice, the way this is going to play out, and again, our original notions of virtual memory, you have to go way back, and we'll go over some things that are even older than the paging we use today, come from a notion of scarcity, right? Where you're, I mean, think about an old mainframe. There are lots of programs that are running. There's not a whole lot of memory, and by not a whole lot of memory, I mean kilobytes of memory as main memory, or a dozen users at once, right? So you really had to figure out ways to share and get utilization up, right? So basically, main memory became a cache for the address space of multiple concurrently live programs. Even if you're only running one process at a time, right? There are a bunch of active processes, some of which just might be asleep and not scheduled in your system, right? There are a bunch of things that need a notion of that mapping. At the very least, they're going to basically be two because the operating system has its own data to manage. And really, how's this all going to work again? This is his review. Trying to do indirection for everything will solve your problem, but it's not going to be fast. So we're going to, again, make use of the fact that you don't need the entirety of your address space accessed all the time, right? So you have the current portion of your program that you're actually executing. You need to make sure that you can find where the instructions are. You have wherever your stack currently is, you have things that are being accessed sporadically in the heap, your global section, right? And collectively, what you are working on right now, certainly if you have a 64-bit address space, is much, 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 much smaller than your address space. Even more broadly, even if on a smaller address space, the hot portions of your address space are much, much smaller than your total address space, right? So caching should help. The same intuitions we had before. We can keep the portions of your entire address space that you're actually accessing in memory, and everything else we can deal with as we need it. Now, let me give you one further caveat. This sort of view that we talked about in, say, 331 of, oh, your user program, and then the OS manages everything, and everything is as it was since the IBM 360, is not actually the best model of what's actually happening. So recall always that the most common computers in the world are not things we think of as computers. They're things like the microcontroller in this device, and they run on bare metal. So they've never had virtualization. So all the IoT devices you're thinking about, depending on what scale they're at, they may or may not have any virtualization at all. So always remember that those things exist, even if we're talking about a different class of machine. And if you are running your code out there in the cloud somewhere, and you are running your code in the cloud, whether or not you've ever thought about it, because if you use a phone, half the code that makes all of your applications work doesn't run on your phone, right? Turn off the internet to your phone and see how well the voice detection keeps working and so forth. And there, your operating system actually usually doesn't manage the resources because your operating system is not allowed access to the hardware. Your operating system is actually a guest. There's actually multiple levels of virtualization that are going on with hypervisors like Zen, the kernel virtual machine. Many people have used WSL2. That's shocking, but okay. So the Windows subsystem for Linux, also built on top of basically KVM style hypervisor plugin, basically put on the Windows side. So in many really modern machines, it's the same story, but 2 levels deep, right? So even your operating system's view of reality is actually virtualized on top of something that's even leaner and closer to the metal. So resource management all the way down. And if you're looking towards the future, an interesting area of research for really about the last 10 years has been, as we continue to integrate more and more devices and build sort of stronger system level models, especially of things like GPUs that aren't CPUs, but are kind of useful. How do we extend our notions of the virtualization of our memory space across what used to be a sort of strict hierarchy of CPU at the top and everyone else, second, to something where I could actually communicate in a mutually intelligible notion of address directly with, say, my GPU, right? How do I do virtualized I/O, right? Also very of interest if you're looking at how do I share devices in the cloud, they want to solve these problems too, right? A lot easier to share one GPU in a system and sell it to multiple people, right? If the GPU actually understands that multiple applications could be talking to it rather than one application owning it at a time, right? So a lot of ongoing work here. This is not a dead area. Virtualization is actually one of the things where you do actually continue to get ISA level extensions and some innovation. There are a bunch of different solutions to this. There isn't a one size fits all. We're going to mostly talk about page management. We will briefly go over some older things like segmentation. But do keep in mind, even though we're going to be talking about fixed size pages, real machines have multiple different sizes of paging, right? They support large pages, small pages, mixed. And if you ever go and take a databases class, you'll find that they hate the way that operating systems do it, and they built their own version of how they want to do all the virtualization themselves, even though they're going to be using the same hardware features that everyone else is. Okay. So if we're going to talk about a vaguely modern notion of virtual memory, it's really fulfilling two functionalities. When we say protection, the other term I would use here really is isolation, right? So there are security aspects of it, but more broadly, it's just about the notion that I can actually meaningfully talk about my own memory space, right? So that I can understand, that even though we are sharing a physical machine, I don't have to worry about modifications to my state from outside, right? I mean, yes, there's lots of other security things that are built on top of that, but the isolation is really what we're talking about here. And the second is demand paging, right? Basically saying that even if my machine only has 32 gigs of main memory, no matter how many things that I run on it until I actually run out of, secondary or tertiary storage, then, I can not just have entire large allocated spaces, right? My 2 to the 64-bit allocated space is enormous, but even the total number of things that are trying to be mapped can exceed the capacity of memory, right? So I can run lots of programs, each of which want to allocate lots and lots of memory, and we'll make it work, right? We'll make it work in the common case, again, caching, trying to make that in the common case at the speed of main memory. Obviously, in the worst case, you'll be running at the speed of moving things between main memory and disk, which is terrible, but at least your program won't crash with out-of-memory errors, but generally still preferable. Address translation, no matter how you end up building it, is what's going to really be at the heart of this. There's going to be some mechanism by which your ISA's expression of what are purely virtual addresses get turned into references to specific physical addresses. We're going to be mostly talking about this again from a CPU-centric perspective. If you're thinking about how accelerators work, if you're thinking about how Intel's proposed DSA, direct streaming accelerators to do memcopy acceleration, these sorts of things work. A lot of those things that are built into the memory hierarchy do operate directly in physical addresses in the first place, but we won't be talking about those too much. Okay, so let's go into the Wayback Machine. And if I'm building a machine which literally can only run one process for one user, I don't really need a lot of support. The only support I could possibly need is for capacity, right? So private uniform, great. And a lot of things did actually operate directly on physical addresses. So while I imagine that very few of you are have ever had the joys of working on a machine running MS-DOS, where you had to go and manually kill programs that were resident in memory to free up enough memory to launch another program, because 640 KB should be enough for everybody, as Mr. Gates once said. You know, there were some challenges, or even also no dynamic relocation was also very fun too, where certain programs actually wanted to use specific portions of your memory, and so you had to kick out whatever was there, or they wouldn't launch as well. So, do you need virtual memory to run a computer? No, but you definitely want it. So let's look at some of the earliest approaches here, which are base and bound methods. Right. So you know, segmentation, base and bound of some approach where you're going to basically have an effective address and some base address. So you're going to grant direct access to some region of memory, and it's just going to be basically offset. So you're talking about, oh, I'm just going to deal in offsets. I'm going to do my entire program in terms of offsets. These are virtual offsets from some base that is unknown, right? And the hardware just needs to sort of take care of this part. I figure out where this is. I got some particular grant for some portion of my physical memory. And as long as it stays within the bound, right? Great, it's illegal access, right? And then the way that I'm going to manage, right, everyone's various memory regions is you get from here to here, you get from here to here, make it work, right? So this is slightly better than just operating on raw physical memory, right? So you're still basically operating on a single contiguous grant of physical memory, right? But now you at least have some mechanism to manage more than one of them and to check if something went horribly, horribly wrong, right? You can talk about swapping these out in this model, but you're going to swap out an entire region or not, right? So if you have a machine that has multiple programs that want to run, it is mapping some subset thereof, potentially a subset that is degenerate and has only one element in it, right? This is still a not terrible way to do business on a machine running multiple processes for multiple users with very limited resources. Yes. Effective address. Yep. Thank you. Okay. So you need a couple of new control registers. You know, not a whole lot of extra hardware. Hopefully, you know, addition and comparison are not going to break your hardware budget. If you can restrict what type of base-bound relationships you can have in particular, even if you want to make this a little cleaner. You know, maybe the sizes of your regions have some power of 2 constraints and so forth. You can then generalize this and then talk about a process being mapped across multiple regions, right? So same idea, still base and bound. A program may have multiple segments, right, for each process. And this is starting to look like what, for instance, say 286 was doing, right? So 286 has, you know, a set of 16-bit, 16-bit effective addresses within a 24-bit potential memory range, and it's operating on top of segmentation. And right, so old Intel machines said, okay, great. I didn't define a very large ISA space, and I need to actually access more data, so I can access a set of small offsets. Right, as many segments as my machine can support. So I'll have one segment for my instructions, one segment for my stack, one segment for my heap, one segment for my globals. And this also gives me a finer grained way to move things in and out of physical memory, right? So I can't run unless all of my segments are mapped, but I can actually start to swap things out piecemeal I don't have to swap out an entire process at a time. If, for instance, I want to briefly run, some daemon or something, right? I don't have to kick out everything from my currently running program. I just pop out one of the segments, go in and go out, right? This has some challenges in that these segments are, it's flexible, but the segments are not uniform in size. So the reasoning about what exactly you want to do, the bounds checking can all be a little more challenging, right? But it's reasonable, right? Similarly, if you're looking at how I want to do, say, multi-threading, right? This is certainly a better model where I can share dynamically linked libraries. I can share my code base. I can split off just the pieces that are separate, right? It is an improvement over just, you get a chunk of physical memory. Okay, so now let's go to what you are all more familiar with. This is the dominant form of virtualization out there today, paging, right? So paging, rather than having, so again, when you think about segments, think that the segments are usually fairly large, right? And have a particular purpose. So all of your code is probably in one segment, right? So paging is going to make a different set of trade-offs. Paging is going to make the unit of allocation uniform and relatively small. So it's going to be very fine-grained, right? You are no longer going to be able to rely on a contiguous relationship between the distances in physical memory and virtual memory, even within a particular type of data, right? So again, in your segment model, the distance between two instructions in virtual space is going to be the same in virtual and physical space because they're all mapped into one segment. In paging, my instructions are somewhere in memory. If I'm not within a page boundary, I don't actually have any idea what the virtual to physical relationship between those distances is. Right? So this, for instance, has already briefly showed up when we saw, what the Intel prefetchers looked like, where they said, oh, well, as long as it's within the same page, we'll prefetch. Otherwise, we'll give up because we have no idea if the data further away has anything to do with the currently running process. Okay. So page frame, usually 4K is a common denominator. There are lots of other options, 4K, 6K, 16K, 64K. And then you get into large pages, 2 meg, 1 gig. Right, so those start to almost look like segments. But because they are fixed size, right, I can play some different tricks. Right, I can have a notion that there is some number of bits representing my page offset, restrict everything to powers of 2, right? And then I can start to play games in terms of how to get just a page number from virtual to a physical page number, and then deal with my offsets separately. Okay. So in a page memory system, abstractly, you're looking something like this. I have a bunch of data. Everything is backed by potentially being in my largest available storage substrate, right? Some fraction of these are mapped somewhere in main memory. They are not contiguous. They are not ordered, right? I have the ability to move them in and out of memory at page granularity as needs be among any number of programs that I'm trying to map. I can also share things at page granularity, right? I can do permissions at page granularity. I have very, very fine-grained control over my memory system. And you might think, great, so, how hard is it going to be to, we need to have this whole separate lecture about caches for main memory and virtualization versus, are they any different than any other cache? Sure, right? We are just caching data for these processes, but the scale of it means that we get very different design decisions, right? I think the right way to look at a lot of problems in computer architecture is you have some principle, right? Oh, principle of locality, spatial, temporal, great. But the way that you want to design a system to exploit it and work well is going to depend ultimately on the constants, right? If I want to move, a 2 megabyte page, I'm going to make very different decisions than if I want to move a 64 KB block, right? If I'm trying to manage decisions over gigabytes of aggregate storage that are accessed relatively rarely, but for which the penalty of missing can be millions of cycles, I am going to be willing to spend thousands of cycles to make a better decision, right? Whereas in my L1 cache, I am willing to spend one cycle. That's my budget to make up my mind, right? Because I need a decision right now. Right, so again, here's the thing that really should stand out in your mind. The penalty for missing in your virtual memory system of going even to the fastest disk that you can imagine is really, really stupefyingly slow, right? Again, how fast is your fastest SSD? Right? Let's say order 4 microseconds, right? Because again, you've got the latency of actually going through the operating system to figure out where is the SSD, because it's not part of your same memory space. That's actually probably about half a microsecond each way. Even figure out where it was and talk to it. You got to go to the PCIe controller. Well, that's some additional latency. You got to actually get the data from, right? But 4 microseconds. And recall that your clock frequency of 4 gigahertz, again, keep it nice and simple. So how many cycles at 4 gigahertz are in 4 microseconds? Right? Here, I'll make this simpler for you. And here's a 10 to the 9th. Here is a 10 to the -6, and the 4 and the 4 are going to turn into a 16. Leave it as an exercise to the reader. It's a lot. Okay. So what we're going to do, right? We are going to throw some hardware at the problem. Right? We all know there's a TLB. It turns out there's actually an entire TLB hierarchy, but right. We're going to do some translation. There's going to be some software structures, hardware support. Great. It's all good. So what we're going to look at here is the design space, because it turns out there are multiple ways you could do this, right? Where and how do we organize the memory that's going to perform this translation for us? Okay. So let's first think about the page table itself, right? Because what we're fundamentally doing is an indirection. How do we store the nature of the indirection? We write it all down, right? There's no grand closed form formula for where your virtual to physical mapping is going to be. Right? So logically, right, you might think about something like this, right? I just literally have a list of all of the mappings, right? And then to resolve this, I could just go look up in this memory structure, right, where everything is, figure out the VPN, add my offset in, right? Then actually go and do the lookup of where in main memory things actually are, or worst comes to worst if it is in disk, right? But we don't want to do that, right? Think about how many memory accesses this would be per instruction. Just remember, instruction fetch is a virtual memory access, right? So even to figure out where my next instruction is, if I did not have any additional support, would require stopping the world, going out to main memory to figure out where the actual data that I wanted is, right? Then going out to main memory to actually go get the data, or even to your cache lookup, right? You're not going to do this. Right? You're going to have a TLB. Right? You're going to cache recent translations, right? So now the TLB is necessarily indexed by a virtual address, right? At the point that you talk to the TLB, all you have is a virtual address, right? So You get the physical address from it, right? And the output is going to be the physical page number. Right? Why the PPN? Because you already have the offset. I don't need to give you the offset from my TLB. You already have it. Okay. As with any cache, there's a space of design choices. We'll come back to that. Right. But broadly speaking, right, you're going to want something that looks more or less like this, where you're going to take your effective address, do a lookup. If it's a hit, then you have the translation. Check if you were actually allowed to access it. And if so, then go on. If, for instance, you do the lookup and it says, no, you can't do that, right, then you're going to invoke your operating system and resolve that. So we're going to imagine that world never really happens from our hardware modeling perspective. If you have a miss, right, then you're going to have to go walk the page table. Now, how long this takes can vary quite a lot, right? So one of the reasons this can vary quite a lot is it may turn out that while the entry is not in your TLB, the translations are actually cacheable themselves. It might actually be somewhere else in your cache hierarchy. You don't necessarily have to go all the way to main memory to get your translation if you have translated it before. Right? So you can cache the page table. Page table is in memory. Memory can be cached. Right? So how long this takes has a bit of variance. Right? Depends on how big your span is. You're going to go walk it. If you're an Intel machine, there's a piece of hardware. That's its whole job. Right? It has to go walk page tables. If you actually find it, great. You update the TLB, return it, resume execution. If you don't, well, you have an actual page fault. Right? This is a TLB miss. This is the page fault. Right? TLB misses happen. They're annoying. They're not that bad. Page faults do also happen, and they're kind of awful. Right? They're really, really, really slow. They're this or worse. Right? Now, where exactly this fits into the rest of your memory access structure, there hasn't been a uniform answer across time. Right? So here are a couple of different designs. Right? So most systems logically, right, figure out what your physical address is and then access your entire cache system in terms of physical addresses. But people have built machines like the Spark 2s where the caching does not involve the translation, and getting things in and out of the cache does. You can do it later. Now, if you're going all the way back to Spark 2, these weren't actually on the same chip, right? So there's various design issues that went here. Now that this and more is all on the same chip, some of the reasons to do this are gone. But the other broader issue is this, right? So why don't you want, in general, a virtually addressed cache? Or at the very least, you don't want much in the way of virtually addressed caching. And the challenge is all about aliases. Okay, so you can see the appeal, right? You prefer to just basically directly, talk to the stuff in the cache. But how you're going to have encoded all the permission data, well, now that becomes cache metadata as well. It's a little awkward, a little bit of overhead there. And much worse, if two programs have different virtual addresses that are pointing at the same physical address. In fact, even if one program has two virtual addresses that point to the same physical address, how are you going to understand that they both need to be updated in this model? Right? How do you understand that there are multiple entries in your cache that could all actually refer to the same physical address? It's quite tricky, actually. So while you can build this, certainly as you look at deeper cache hierarchies and you look at the interaction with a lot of other pieces of modern computation, this is usually not a desirable set of trade-offs, right? Unless you had a lot of restrictions on ensuring that your cache is alias-free, right? Which would require quite a bit of bookkeeping, right? Then this is not an appealing approach. right? Certainly would be very, very difficult to do in, say, a simultaneous multi-threaded processor where you would logically want to be able to have multiple valid mappings going on the fly in one cache. In general, any time that you might have to update multiple copies of things, you should think long and hard about whether there's a better way to do it. Okay. So great. So we know TLBs exist. All we need to do is just add a TLB and everything's going to be fast, right? Not exactly, because there's one more little wrinkle here. This is what a page table looked like in 1986. It don't look like this anymore. So this is still showing you a 32-bit, so it's a fairly shallow one. But a modern 64-bit page table is not going to be flat, right? So let's actually go back. Think about this lookup here, right? If I have a 64-bit address space and I want a flat page table, how big is my page table? So let's say I have, okay, that is too small a piece of chalk. Let's try again. So if I've got an address space of 2 to the 64 bits, I've got a page size of, say, 2 to the 12th, right? How many pages are there? Yeah, 2 to the 52. This is what we call a reasonably large number, right? Yeah. Also, if you want to simply factor this, if you don't remember your SI prefixes, right? 30 is your Gibby, 40 is your Tibby, right? This is the next one up at 50, and it's 4 of those. Okay. So that would not actually fit in your main memory to have the page table, hence something like this. Any reasonable approach in translating these large address spaces is going to organize your page table in a way where the amount of storage you have is proportional to the amount of physical memory that is in use, not to the total size of your address space. The page walks are a little more complicated these days. Yes? I mean, no, it's a different sort of structure, because here you're actually carving off bits of the address. Yeah, so this is a sort of progressive localization, right? So here you would basically take the upper bits to index into this page. You have one page of data pointed to here, right? So this register has to exist, and at least one page of data is mapped. So at least the first page of your page table is pinned. Good job. Right? This is not swapped out. Otherwise, you wouldn't be able to find anything. Okay. But from here, right, you're going to say, okay, I'm going to use these 10 bits, right, to index into all of these entries, which are pointers to some other page. Right? Why 10 bits? If you've got a 12K page, 10 bits gives you 2 bits. Each of your addresses is 32 bits. If you had a, so you can get 2 to the 10th entries in a 4K page if they're 32-bit. If you have a 64-bit addresses, you're doing your number of entries per page will drop a bit, right? Okay, and we get 2 to the 9th. Same idea, right? So you're going to carve off these bits to index into this. That will tell you where to go looking, right? So each of these are the set of entries. It'll, again, there are many more than 4. I'm just not drawing all 1,024 of them, right? These will index into one of these. Again, any of these individual entries may in fact not be mapped, right? So logically here, if I'd index into this, it would tell me, yeah, actually, no. This page doesn't actually have a valid mapping. So this would cause a page fault to load in, right, the next piece, which would cause a page fault to load in the next piece and so forth. Right, so if you actually demanded something down any particular path, you would bring all the necessary pieces in, right? But only to the portions that you're actually currently accessing. You don't have to pre-populate it for the use of your address space, which again, if your address space is this big, I guarantee you, you're not using most of it. Right? Your usage is sparse. Right? If you are, in fact, actually using and running out of space in your 2 to the 64-bit address space, well, the supercomputing deadline is on April 6th, so submit your papers accordingly. So a little more complicated. You got to walk through this. So the time it could take to resolve, as I said, a TLB miss, highly variable, right? In terms of how, does it just take a walk through all these? Are any of the pieces that you're walking through already cached, right? So you can actually have some dedicated caching for multi, to help the page walk itself, right? Now that you have these multi-levels, and you can associate them in different portions of your memory system. For a modern machine, your depth is usually about 4 or 5, right? Depth of your page table. And again, if you're looking at something like Intel, where there's a hardware page walker, you have some constraints in terms of what your page table could possibly look like. There's a piece of hardware which is going to walk it in a certain particular way. If you're in a system with a software-based page walk, you can be a little more flexible. Now, when I say the depth is 4 to 5, again, that's the sort of depth of a page table, but your page table might be not actually mapping to actual physical addresses if you are a guest OS on top of a hypervisor. So in the worst case, the depth of traversal basically is going to be that depth, you're going to run proportional to the depth squared. All right, so if I have a guest OS on top of a hypervisor, and I have to walk the entirety of my page table to resolve it, nothing is cached, right? Actually, each of these might actually cause a walk all the way through the actual hypervisor's page table, right? So you can get like, 24 misses to memory to resolve a TLB miss if you get really unlucky, right? Because each of those things could be all the way out to main memory if they're not cached, right? So there's actually a lot of work on adding additional support and prefetching and other features to make the page walk itself faster in our new highly virtualized shared resource machines. Right. So if you're a cloud vendor, you think it would be great if we pushed a little harder on making these better. The other thing is that the TLB we said is a cache, so we can do the same tricks that we did with getting our miss rate down that we did for our data instruction caches. So any chip you buy today has a multi-level TLB, right? So that first level of TLB has a lot of the same constraints for latency that your iCache, your Dcache have at L1. So you can't have a very large TLB with very large span. It stores a lot of translations. That's okay. I can have an L2 TLB. An L2 TLB can have 512,000. I can have a lot more entries. I can even have an L3 TLB if I really wanted to. If I have a multi-core machine, I can even look at whether I want to have shared resources the same way I have shared caches between multiple nodes. And as I mentioned, increasingly as we look to support virtualization for things that aren't CPUs like GPUs, right? These sorts of things actually become even more useful, just because of the nature of the work that actually gets scheduled to GPUs, where lots and lots and lots of threads have very similar access patterns. So again, in addition to the specific page walk caches for the page walker, if you're looking at things that actually you can get good prefetching on, it'll turn out that pieces of the page table actually have reasonably good residency in your shared L3. Right? And there have been a bunch of works that have looked at whether or not you're going to get more mileage out of optimizing the page walk or just trying to keep more of the page table that is in use resident in your shared memory system. So a little more complicated in reality. Okay. So the two models that we're going to ultimately go through, right, when we're not walking, we're on our just accessing the TLB itself, are either a physically indexed cache or a virtually indexed cache. And again, we said we're not going to have a virtually addressed cache because that has aliases, other problems, right? But the indexing is still a design space that we can play with terms of the allowed parallelism between the cache lookup and the TLB access. Right? We're not going to be able to resolve a hit until we actually get the address either way. We need the physical address. Right? Both these things are physically tagged, but we can do a either TLB first approach, which really sort of decouples the design of this cache from the address translation, but it also serializes it. Or we can have a virtually indexed cache, right? So the most common thing that you're going to see in most designs is a virtually indexed, physically tagged, or VIPT, right? Structure with the TLB and the cache being indexed in parallel, and then only co-serializing on the actual final hit logic, right? I can do this as long as all of my index bits come from within my page offset, right? Then I can immediately dispatch them to my cache. Now, I can actually do things that aren't strictly that. So it turns out you can actually still build a virtually indexed, physically tagged cache, even if your index exceeds the page offset, but you need a little help, right? You'll need some guarantee, for instance, from the operating system about how it maps contiguous pages, or you'll need additional tagging support so that you can identify that an aliasing situation has occurred and clean it up. So there's some tricks you can play here. I'm not going to spend too much time on it, but if you do the math, for instance, on Core i7, right, you would see that they're clearly doing at least some tricks, given the associativity that they have and the size of a page and where those index bits are going to have to come from. Okay. So if you do have synonyms, right, and since we don't want aliasing because aliasing is bad, right, then we can make it so that the associativity is the way that we grow things rather than the number of sets, so that we don't use more index bits for larger caches, right? That has a cost, obviously, right? Or, right, we have to have some sort of external guarantee where that invariance is going to be reinforced for us, so that we at least have, for some small number of A bits, right, a better way of doing business. Okay. Now here's just a couple of examples of how prior systems have resolved this. Right. I won't, as I said, dwell particularly on this, but you can go and look at these slides later. Right. Okay. So TLB is a cache. It has its own design space. Right? How associative do I want it to be? How big do I want it to be? If your TLB is very highly associative, you might use CAM logic. Right? That certainly was popular in certain periods of design. And while it is relatively small, right, it does keep getting a little bit bigger and bigger, as I said, with all of the security protection bits being bolted onto your TLB. So if you look at a modern TLB, it's not just going to be a valid virtual page number, physical page number, some replacement logic, and whether or not it's been accessed. There'll also be some set of protection state bits that are here as well. Right. So how many people are familiar with buffer overflows? A little bit, kind of, sort of. Yeah. So one of the old common patterns of buffer overflow was that you would do a code injection. Right. So back when this TLB entry looked, well, more like this, right? Didn't have additional protection bits. I'm going to read in some data from a user, and that user might just dump in, it's a pile of bytes. They might dump in code. And if I can tweak the return address to point to the code that I just gave you, I can start executing arbitrary code. Right? And people decided that was a bad idea. They said, okay, this is a simple fix. Right? We will just make the stack non-executable. We will say whether any given page could possibly contain legal code. Note that we still have buffer overflow problems, right? It hasn't fixed all of our issues. One of the particular reasons, this is a bit of an aside, but I do find it fascinating. How many people have ever heard of return-oriented programming? So it will turn out that you don't need to inject code into the machine. There's plenty of code already there. You just have to be clever about executing code that is already part of your program to execute arbitrary functionality. And by, I mean plenty of code, I mean even libc, which is not very big. If you are particularly perverse about setting up the values and return addresses to jump around within it, can be used to build a set of widgets that are Turing complete. There's an entire discipline of how to, even on, say, a machine with read-only memory, you literally can't execute any code that isn't there because it's a voting machine and there's a ROM. That's okay. You can still actually figure out how to exploit even the minimal amount of code that's there to execute completely arbitrary code. There's a lovely printout from a Diebold machine that was pasted to the door of the security lab for a while, showing the results of the first American election between Benedict Arnold and George Washington, where Benedict Arnold won the landslide, clearly. All right. No, Diebold was not used in the 1700s. Okay, so if you're looking at how this is modeled in say, simple scalar, right, it has a set of cache parameters that you'd set up the same way you'd set up any other cache. Simple scalar doesn't model complex, additional permission bits because, well, it's simple. Okay. So again, if we look back to how we want to use these, right, this does put some limitations on how big our TLB is going to be so that it is not on the critical path here. So do keep in mind that in practice, your TLBs are going to be fairly small in size, right? So 32, 64, these are pretty reasonable sizes for even a modern L1 TLB. If you want to go further, you do the same thing you do, cache hierarchy, go deeper. Right, so simple logic, block offsets, physical page number lookup, groovy. But again, if you do not have a fully associated TLB, do recall that you do actually need to pull out indexing from within here, figure out where to go in the TLB. So in terms of how the TLB and the virtual memory system interact broadly, you can think about 9 possible combinations right here of TLB, page table, and cache hits and misses. Not all of them are possible. So I can hit my TLB, my cache, and then I won't have to have gone to my page table because I hit my TLB, but it must be there. This is legal. This is what we want. Great. This is also perfectly fine. I know where this is. It just isn't in my cache. This is also not too terrible, right? The data is there. I just don't know how to name it. I'll go look up, get the name, and go look up in the cache, right? Again, not what we were hoping for. We didn't know where it was, so we had to go and deal with that on the TLB side. Then once we knew where it wasn't in the cache either. Oh well. This is what we would like to minimize. These are page faults, right? If I look it up in the TLB, it's not there. I look it up in the page table, it's not there. And it is in fact also not in the cache. This is a legal state of the machine, right? But it's undesirable. These other two, however, are not legal, right? The TLB has a strict inclusivity property with respect to the page table. You cannot have a mapping for something that is not actually in your memory. That would be bad. So when your operating system changes, remember, software manages what is and is not in memory. When your operating system decides to change these mappings, you'll experience what is called a TLB shootdown, right? So your entries will not be replaced. They will be externally invalidated, right? Any change to the TLB mapping, basically, rain will fall from on high and sweep away all that you know, right? Sometimes it's not even terribly specific. It may just invalidate the entire contents of your TLB. That would be sufficient. Okay. Similarly, right, you are not allowed to have data in your cache be valid for unmapped pages. Right, so you need to take care of this invalidation property for all of the contents of your caches for things that are in fact not mapped in memory. Right, so while you may have a variety of inclusivity properties that hold between your L1, your L2, and your L3, recall that it is always the case that anything in your caches must be in main memory. Right? These systems are not going to work properly. Invariants are too hard to keep track of to deal with things that are cached, but not actually currently mapped. Right? Again, the other way of looking at this is your cache is hardware managed. It needs to be able to send things on through the hierarchy using physical addresses that may eventually end up in memory. If there's nothing in memory to receive it because it's not mapped, hardware has no means of understanding that this has even happened. So it is software's job to make sure, right, that the appropriate external invalidations occur to enforce this. So here you again, we'll see one of the cases where an external event, i.e. a software manipulation of an in-memory structure, might affect your cache independent of the replacement policy. Right, so invalidations will come from outside for other bookkeeping purposes. Okay. So here are a couple of just real examples. Again, these are reasonably old machines, but they give you insights into what you're playing with. Right, so the page size on an old Intel Core i7 was either 4 KB or 2 or 4 megabyte. So it did have very page size support. Even this ARM Cortex-A8 actually had a bunch of different page sizes that were supported. So this has L1 and L2 TLBs. The L2 TLB is unified, has separate ITLBs and DTLBs, right? And you're seeing here 128 or 64 entries, so not terribly large. Again, do the math. If I have 128 entries and 4 KB per page, right, that's not a whole lot of memory that I can, know the names for and keep close. My working set from the TLB perspective is fairly small. Smaller actually even than my entire cache hierarchy. Right? It is usually the case that your cache hierarchy can have a larger span of things than your TLB can actually keep the translations for close. It's just sort of the way that these things have grown. Okay. You may have different number of entries for small pages and large pages, whether those are actually physically separate TLBs or whether they're different configurations of the same TLB, whether you can support both large and small pages at the same time. Your mileage may vary. Okay. Now, if you look at the size of the address space, right, you'll note that the physical address space and virtual address space may not be exactly what you thought it was. So when we talk about 64-bit address spaces, a lot of actual real machines really had 48 or 49. And so you get all sorts of, if you go and read the actual specification guides and you say, well, what's in those upper bits? Some of them define them to be undefined. Some of them define them to be zeros. Some of them reserve them for future use. The RISC manual is interesting because the RISC manual, the RISC-V manual, actually supports a bunch of different virtual memory sizes for the variety of device spaces it's looking for. And those impose different page table structures accordingly. Right. Okay. And again, as I mentioned, handled in hardware. So 64, 32. If you recall the size of the cache here, right? So 4 KB pages and 8-way associative works out for your 32 KB cache for the D cache. 4 KB pages and 4-way associative doesn't actually do the math for your I cache for Intel i7. So you do actually have some restrictions on where the instruction pages are mapped. You would have to map 2 at a time to make sure that you don't have aliasing effects That's not too hard to do for code. Excuse me. Okay. So broadly, right, keep in back your mind, TLB is a hardware structure, right, which is just there to assist this virtualization process, right? And the virtualization process is there on behalf of the software, right? I could run everything bare metal, right? At some level, something is running bare metal, right? When your machine boots up, there's no page table, right? So your BIOS is running bare metal. Even your hypervisor, certainly has to reason about the physical addresses of your machine, right? But for everything else, right, your common case is that some piece of software wants to talk about having a nice, simple, uniform address space of bytes, not a complex hierarchy of page translation, which may or may not be in memory and might possibly on I/O devices that the ISA doesn't even understand really exist, except as I sent some data, I got some data back, right? You don't want to have to write that when I want to just do X equals A of I. I want to write X equals A of I. I don't want to do the rest of this stuff. The hardware is going to help you. Take your operating system class to figure out, all sorts of other fun with page table and its organization, security properties. But you do get a lot of interplay, right, between hardware and software here, because this is the hardware system that is going to be responsible for at least keeping track of any new security features that you put in. So you do have to sort of get agreement across that interface if you want to play around with it. We're not going to go into the particulars of disk placement, how you deal with boot up when you don't have virtualization yet, how you deal with these other sorts of issues. There are some design constraints, but they're not really big. If you want to sort of think about, again, the environment that this is designed for, right? Our modern computing environment, there are going to be lots of processes. Again, open up, your machine of choice, run top, or, open up the, I don't remember what they call it off the top of my head in Windows that tells you how many processes are running. Task manager, thank you. And you'll see that there are a lot of active things, even when you're not doing much of anything. Right? By the time that your system boots up and you can launch that to check how many things are running, there are probably at least a few hundred processes that are active. Right? If you have too many Chrome tabs, you may have even larger number of processes that are active. So real machines are sharing a bunch of resources. They're managing this at very fine grain. And the good news, right, of living in the age that you currently are in, is that while we still have resource scarcity compared to our address space, we don't have the resource scarcity that we once had, where you could hear when your computer ran out of virtual memory, right? So back in the days of physical spinning disk hard drives, I could tell you exactly when, right? Not just because I stopped being able to use the machine because everything ran 10,000 times slower, but I could also just literally hear the clicking of the hard drive as I started to run out of physical memory, something that between SSDs, you can't hear flash memory. If you begin to hear flash memory, take less ayahuasca, right? Whatever. If you begin to hear your flash memory, see your doctor. But also, you buy a machine today, it's 16, 32 gigs of memory. Most things you're doing aren't going to run out of the physical resources. Your notional scarcity is very different. Now, there's still plenty of programs that can chew up most of your 32 gigs of memory, right? If you run FPGA synthesis for non-trivial designs, you will be out of memory, right? If you are doing large graph analysis, you are out of memory, right? I was chatting with someone at NIST, where the individual files that they were loading for some, I think it was like scientific, visual instrument data, right? And a single image was larger than memory. right? They were, again, working on some supercomputing sort of stuff, right? So scarcity isn't gone, but understanding whether it is still the common case is an interesting thing to think about in the back of your mind. And there certainly have been proposals to, for instance, bring back segmentation for machines like key value store boxes in the cloud that really only run one app 99% of the time, right? So there are racks and racks and racks full of machines where only one process that isn't the operating system is running. And honestly, if you want to make it a little leaner, only one process is running. You don't even need the operating system if all you're really doing is just running a KPS. So again, interesting areas of work continuing, not a dead area, especially with respect to GPUs, sharing, I/O, so and security also very active here, right? So I'll end this with a standard sort of lookup problem, right? At least you should be able to understand the logic of this and think about how you would extend this for a more complex machine. So here would be a machine with one level of DTLB, one level of L1, right? If we tell you that it's VIPT, you know that you can do the indexing mutually, right? But you're going to need to look up the rest of these bits in the TLB to figure out which of these things you were actually accessing. You could wander through these. You could also extend this, right, and say, okay, what if I had a multi-level TLB? Right? How would this change if I had a two-level TLB? How would I handle a miss? The same way I handle it in a two-level cache. Right? I'd be able to do the lookup and say it's not there. Then I go to the next one, but the next one might have a different organization, right? And so that organization might have different indexing, might have different subdivisions of my bit pattern that I am presenting it to do the next lookup, right? They're not constrained to be similarly organized. And then what would I do with my L1 TLB after I went to my L2 and I hit? I would replace the entry. I would update the replacement bits, right? It's a cache. Same policy questions here. All right, so we'll leave it a little early today, and that will be all.